This video is intended to walk you through setting up your PD2. PD2 is a Schlumberger software used to optimize hydraulics for each rotary steerable. When you first open PD2, you're prompted with a Run Details window. This gives you the option to input things such as your rig name, job number, run number, basically just to help organize your reports. None of these inputs are used for calculations, so we'll omit this part for now. Once you get into the main screen, you'll notice there's an option for inputs on the left, and then based on those inputs is a row of calculated outputs. So we'll just start with the inputs and fill them out from top to bottom. Our first option is a tool selection. So if you notice here, PD2 has the ability to set up hydraulics for any rotary steerable in Schlumberger's fleet. So you want to make sure you pick the correct tool type and collar size. Next is your ball sleeve radial gaps. So in the orbit, there's 3 pads. Each pad has 2 balls that actuate it. These balls have a housing or sleeve that they sit in. And for each bias unit, the shop will measure the clearance between the ID of the sleeve and the OD of the ball. They'll take those values and input them into the OST. So you want to make sure that the OST's bias unit serial number matches what is physically stamped on yours. Once you've confirmed that, go ahead and put your values in. And while I'm putting these in, it's good to note that sometimes the bit hand will show up to location before your tools do. And if he's asking what kind of jet you want, if you want a rough estimate of what you need set up for your pressure drop, you can just input 0.06 for all 6 values. Like I said, this will give you a rough estimate and get you close, at least to set up your nozzles. Okay, continuing down the list is a define sleeve grooves checkbox. So this is for North American land specific jobs. Globally, the design, as you see here, is a little notch or groove on the sleeve. North American land has decided to phase out this design, and they incorporated this into their PD2 calculations to account for it if it showed up on your bias unit. So in general, these will all be 0, but it's a good thing to check and have some sort of background knowledge of. Your pump flow is going to be 650 for this example. Mud weight, bit diameter. Next checkbox is a fluid bypass reamer. This is there to create the scenario if you have a tool above the BHA that communicates to the annulus. So a rhino reamer, a well commander, anything that is designed to have some sort of fluid leakage, the vendor needs to supply you with this estimated percentage. Next is RPM. So this is your bit RPM, not your surface RPM. So surface plus revs per gallon of your motor. Nozzle sizes, for this example, we use 412s, 214s. If you'll notice, our total actuator pressure drop, this box is now green. So this is the ultimate goal, which is to get our pressure drop within the predetermined range for a 675 orbit, which is green here, so that means we're in the recommended range, but we're not completely set up yet. Since we're running Vortex, which is a fancy way of saying there is a motor above the power drive to assist with our bit speed, we have to account for the fluid leakage in it. So we check this box and then select our motor type, which is basically a catalog for Schlumberger motors. In North American land, it's very common to run a third-party motor. In this scenario, you'll select manual entry, and then that vendor will need to supply you with their leakage percentage. If you're running a Schlumberger motor, for this example, we'll use a 7-inch Dynaforce 7850. There's another list of inputs. Next is if you're running an MWD below the motor. So you want to select the correct MWD type and collar size, and then fill out your anticipated mud parameters. And then our last option is a motor radial bearing clearance. So these are defaulted for a brand new 7-inch Dynaforce with this power section. It's very rare that you get a brand new tool. For the most part, this tool will have been run, refurbished, realigned, and sent back out. In this scenario, they'll be sent out with a build-out report, and that build-out report will have the correct upper and lower values, so you can input them here. Okay, so we're all filled out for the vortex assembly now, and if you'll notice, our box is orange now. If we read our little warning, it says the pressure is close to the lower limits. So basically this is saying we're now underneath or below our optimal pressure drop. Okay, so this is because we're accounting for leakage through the motor. So basically, if we would not have selected this and went downhole, we would have undershot our pressure drop. So since we are below the recommended pressure drop, we need to decrease our TFA to increase the pressure drop. So you can do that one of two ways. The first way, and the preferred method, is to change the nozzles in the bit. So if you lower the TFA, you can start to build up the pressure drop here. So you can see we're more towards the middle of the recommended range. If the client doesn't want to do that and they need to use those specific nozzles, you have the option to add a flow restrictor in the power drive. So in this scenario, you can just play with your restrictor sizes until you get within your recommended range. Last thing to notice here is that if you can do it with your nozzles, then you'll select none here. If you do none, then the restrictor body does not go in the power drive when you pick it up. Okay, and I mention that because there's a 32 option here, and this is just the nominal sizes of a jet. You'll see 32 out of 32, and if you select this option, then you'll need to put the flow restrictor body in the power drive with the dummy or 32 size restrictor. Okay, so we're in our pressure drop. We can look at our calculated values, and we'll notice the top section is basically just a summary of our inputs. Next we have the pressure drop section. You can see the flow restrictor pressure drop plus the bit pressure drop is the sum of those is the total actuator pressure drop. Working on down the list, you have your TFA and your hydraulic horsepower for the bit. And then the last thing I want to touch on here is your orbit force on formation. So there's two ways to kind of show how much force you're having with your pads. And that's the pressure drop, which needs to fall within a predetermined range, and the force on formation. So this force on formation depends on your ball sleeve radial gaps and the area pushing against that force on the formation. So this number is more of a localized area specific number. So you want to make sure your pressure drop falls in the correct range, and also refer back to your coordinator or drilling engineer that might have localized experience and know what force on formation works in your specific area. So once you're all done with PD squared, you have the option to save it. And when you save this workspace, throughout the run, if you want to open it back up just to change your different flow, you can without having to reset up the whole sheet. The last thing is a sensitivity analysis. This allows you to put a range of parameters in. And then you hit generate. And you can use this to communicate with your drilling engineer or the client with a nice summary report of your hydraulic setup. So the top is the header information from the run details that we omitted. And then the rest is just a summary of our setup. You can see your total actuator pressure drop here. So this is what you calculated. And the second page is your sensitivity analysis. So it'll look at the range of flow, mud weight, and RPMs, and then color the box in for the accepted flow ranges. You can see the dark is your red or not recommended. The light gray is warning or you're close to out of the range. Then the white is your optimal ranges. So as we bring this PD2 video to a close, there are a few key points to remember. Number one, confirm that your OST's bias unit serial number matches what is physically stamped on your tool. Number two, confirm your drilling program ahead of time. So whenever you get the tool, you need to confirm what your flow and mud weight is expected for that section. That way you can set up PD2 and inventory your available restrictors. If you're going to use one and you've set up your PD2 but you don't physically have it on location, that doesn't really help you. Last, remember the difference between pressure drop and pad force. So pressure drop is just the pressure across the bias unit that needs to fall within a predetermined range. And your pad force on formation is dependent on your ball sleeve radial gaps, and it's more of a localized knowledge. So on this specific rock, we know that this pad on formation is optimal. So hope this video helped.